right, we got to move quickly today because we want to get out and be able to do some running here after this. So today we're working on linear motion. So linear would mean what? Straight's close enough. Now there are some other different terms there that you're going to need to know for your quiz that's coming up here. So what we're going to work on is things that influence a person's or object's acceleration, how to measure that linear motion, that's what we're going to do outside, speed, velocity, a projectile motion, which, well, since there's so many of us here, I'm going to have some of you play catch, and I'm going to see if I can figure out this app that I got last year that would figure out how fast you're throwing the ball. So it's like, one, you're going to do it actually by hand, like actually calculating it off of a video. And the other one, we're going to see if an app can do it for us. So we'll see how that goes. The factors that describe projectile motion. So speed. Now, this is an interesting term. Speed is a scalar measure. Anybody know what scalar mean or scalar? Scaled. There is a number on it. So it is a quantifiable measure. There's usually, in our world, it's all in miles per hour. A lot of places it's going to be, but in most of the world, it's in kilometers per hour. That's going to indicate how fast something's going. Sometimes it'll be in like meters per second. Like I said, there's like an Academy Days thing going on upstairs, so it's going to be noisy. So it can be measured by generally dividing the length or distance by the time traveled. So speed does not quantify the direction. So it doesn't say whether you're going forward, backward, left, right. Speed is just a scalar number. It doesn't say whether you're going north, south, east, west, whatever, like that kind of thing. So, for example, an elite sprinter runs 10 meters in, we'll just say 10 seconds to make it an easy number. We know that in athletes that the distance is 100 meters or 109.4 yards. Did you guys know that was different? And in the certain time we're going to use is 10 seconds. So from this information, you can take the sprinter's average speed, which is 100 meters divided by 10 seconds, so 10 meters per second. Or if you converted that into kilometers per hour, that'd be 36 kilometers per hour, or 22.4 miles per hour. We'll see if anybody gets anywhere close to 22 miles per hour today. So your velocity, I kind of like, I use this, now I was a math teacher for a little while at one point, so I apologize if I go a little too nerdy into the numbers here, but that is part of the fun to me of biomechanics. So I used this triangle for all of my geometry, Algebra 1 classes for figuring out velocity. So it's easiest to think that displacement is velocity over time. So what that would end up being, so if you're trying to find velocity, you're going to have distance over time, or displacement or distance over time. To find time, you go time is distance over velocity, and distance is velocity times time. So I like that it was a triangle there. It makes it real easy to figure out which one you're dividing by what, depending on. So that's just a fun way to do it. I think that is an easier way of remembering that. Velocity, on the other hand, is the position divided by the amount of time. So this tells us in which direction and how fast. So remember those terminologies there. You're going to have a question to say, define velocity, and it's going to have something about, it tells you what direction, and one of the other answers is going to be speed. It's going to give you, just make sure you know the terminologies there. So when kicking a ball, you can look at how fast the ball is traveling as it takes off in a horizontal or vertical direction. And so to measure how fast the ball is traveling, we measure these results with two components. So we measure how fast the ball travels in the plane that we want, and then we will measure velocity, not speed. All right, so I put all the numbers on the side here. This is a kid measuring, it looks like at his house, farm kind of thing. So like ingenuity to this kid here. I almost made you guys do this too, but I decided against it.
How do you record the speed of a pitch without using an expensive radar gun? The answer is a series of relatively simple math problems. First, you're going to find the distance in miles. The distance is how far you're throwing the ball in miles. In other words, how many miles are you throwing the ball? The second is time, in hours. How many hours is the ball in the air for the distance that you're throwing? And third, you're going to find the speed of your pitch. Starting with distance, I chose 20 feet, but you can choose any distance. It can be 60 feet 6 inches, it can be 20 feet,
That would be a
it can be
pitcher's
30
mound.
feet, doesn't matter. So then you're going to take the distance you threw the ball.
So that's why I put that here.
And you divide that by the amount of feet in a mile, 5,280. So 20 divided by 5,280 is about 0.003787. The most accurate way to find the exact time of the ball between the distance you're throwing it is using slow-mo camera. Slow-mo records at 240 frames per second, which is 8 times slower than 30 frames per second, which is the normal video speed. So when you record in slow-mo, you stopwatch it, and what you get, you divide by 8, and that is the amount of time. It's 8 times more accurate because there's way less chance for human error. Using slow-mo and the stopwatch, I got 1.3 seconds. Now I divided that by 8, and I got 0.1625. Now you need to find how many hours is 0.1625. To find that, you divide 0.1625 by 60 because there's 60 seconds in a minute, and then divide that by 60 again because there are 60 minutes in an hour. Your answer should be about 0.0000.
Oops. I put the wrong number there, but yes.
Now to figure out the speed you're throwing the ball. First, you take the distance in miles that you're throwing the ball. That was 0.003787. And you divide that by the hours you're throwing the ball. The time in hours is 0.00004513. Your answer should be 83.9131. I rounded 83.9131 to the nearest number, and I got 84 miles per hour. So I can pick
Pretty solid throw for a teenager, it looked like. Nice high leg drive. It's a pretty good throw there for throwing it right next to the camera.
Make sure to comment your...
All right, so I'll say we will try all this, but we're going to probably do it. We're going to do it with running splits rather than throwing a ball. It's probably a little tougher. So there are other ways you could do this. We started this a little bit in our strength lab, is you could do velocity based training. Don't think we're going to go 6 minutes into this one, but we'll hear what he has to say for a
Anyone that
minute.
takes the training seriously knows that to make progress in the gym, it's largely a game of numbers. Sets, reps, and loads, we manipulate these variables to adjust the training outcome. But for me as a coach, these numbers really only tell me about the volume or the quantity of my training. How much did I do? They don't answer that really important, crucial question, how well did I do that set? When it comes to measuring quality, coaches and lifters have largely relied on subjective methods, RPE systems, eyeballing sets, or getting a feel on how a movement's going. I believe that velocity is the missing metric in your training. When used well, velocity tracking can unlock a whole range of metrics and measures within your training. Fatigue, readiness, auto-regulation, intent, all these factors can help drive training outcomes and improve your performance. Over this series, we're going to explore the fundamentals of velocity-based training, diving into what makes it such a useful tool for coaches and athletes alike. Let's take a look at a simple application of velocity-based training in practice. Here's 2 sets of a trap bar deadlift, both with 100 kilos, both for 5 reps. Which set do you think had a better strength and power adaptation? Now, a good coach might be able to tell that set B is a little more explosive, a little poppier than the first set, or set A, but by how much? When we use velocity tracking instead of guessing, we start to really see the difference and how much of a difference there is between these sets. From the data, we can see that set A has a velocity, or an average velocity across the set, of 0.59 meters per second, while set B was up at 0.7 meters per second. Now that's a 16% differential in speed. That could be as much as 5 to 10 centimeters on your vertical leap, or a third of a second over 20 meters on a sprint. Now, when it comes to training, you wouldn't train at, say, 84 or 85% on your sprints and your jumps, would you? You'd train with all out maximum intensity. And the same rules apply in the gym with your lifting.
All right, so let's just give you a kind of a preview. So those are other places that we can use velocity in sports and in your therapy sessions. That's probably one that wouldn't be a bad place to be doing that, especially if you're doing personal training with somebody. So acceleration, so that's going to be acceleration or deceleration, is the rate in which the velocity or speed changes. So that velocity of a sprinter earlier of the 100 meters was 22.4 miles per hour. That really doesn't tell you the actual top velocity, because the top velocity could be as high as 26 miles per hour. Right? They didn't hold that exactly the entire time. So how much of an athlete's velocity increases or decreases depends on the rate of acceleration or deceleration that you have. So here's kind of an example spreadsheet, and this is what you're going to come up with here for yourselves here in just a little while. Is you're going to have the distance and then however long it took you to get there, which you're going to use video, probably sliding your finger on your phone to figure it out, if you can actually start it at the right time. And I actually do have a Excel sheet made for you, so you don't have to make this this part's all in there, how far it is, all that's already there. So you just have to type in the numbers, and then you have to come up with a little bit of Excel to get those details in there, which you just got to follow a video to do so. So there's ways to do this. The best way would be to have timing gates. So, I mean, if we could do this as perfect as possible, I'd have, for these 50 meters, I'd have 6 things out there, one for the start, and then every 10 meters, and you could actually get very detailed to the exactness of the timing that somebody goes. You can use video, which is what we're going to do today. Would be really cool to have radar. I was looking around here last year to see, would there just happen to be a radar gun? If there was a baseball team here, I'm sure they would have had somebody sometime would have had a radar gun that we could have probably used for this class. GPS would be a really interesting one. There are a few apps. I've got one that I want to try for throwing a baseball. I was working with somebody last year on a soccer ball that you would set up your app on a tripod, and then here's where someone's kicking, and then here's the goal. And it would actually give you points. You could set up, here's the goal, and you could say which spot is worth how many points in the goal, and it would keep track of your score and the velocity of the ball going at the same time. And I still get things from my phone because I forgot to turn off the things there. Was it alerts? So I keep getting once a month, it's time for a new kick from this My Kick app. Anyways. So linear motion occurs. So this is for an object to move or remain stationary. There needs to be some sort of influence or force. Usually that's the muscles throwing or moving the object. A force is a push or a pull that changes or tends to change the object, the shape or state of motion of the athlete or an object. So either your muscles moving the ball or maybe the object you're swinging hitting the ball. So when an athlete performs a sports skill, the athlete primarily produces internal forces within the body by contracting muscles, which result in the external movements that you have. So vectors, so that's what this is going to be. When the direction and the amount of force applied are known, we can combine these into what is called a vector. So the term vector simply means to quantify that it has a direction. So it's basically velocity with a direction is a vector. So force vectors represent diagrammically usually by arrows. And then the head of the arrow indicates the direction, and the length is how much force it is. So when we were watching some of those videos, somebody had one in their presentation last week of like where the foot hit the ground, and it would have a force arrow of what direction it was going. That's why it was giving the length of that arrow was actually how much. All right, I need a volunteer, or two. Actually, I need two. We're going to try moving this. All right, here's one. We need one more. There we go. All right, so you're going to stand probably kneeling behind those cones. Yep. Well, because it's going to be easier to do it lower to the ground. And we'll see if we can get it to work here. So the two of you together are going to be two different vectors. So you have to pull it through the cone and try to get it to stay on the blue line. This was way easier than I thought it was going to be. Oh. All right, can you? Yep. Back to you there. All right, I want to see, can you make it, can you take it to the side, to the side, to the side as you're pulling? So one person, so to do it straight, they had to pull the same amount. Oh, I wonder if this can be a problem. I'll tell you, don't spill my coffee here. All right, can you pull it more that way now? Now he's changing the direction, the force, changing the vectors. It's not the best example, it's not the best floor. It probably would have been better to do it like I'm on here, but that was fun. I like having random objects in my office turn into an experiment. So that was what this is diagramming here, as you would have how much force is going here to here, and in this case, to make it go on a straight line, both of these vectors need to be going the same direction. Where I see this the most often is in a jump shot. It would be simplest to shoot a jump shot with only one vector, correct? So why don't we have people shooting with just one hand? That's only one vector. You'd think it would be simpler, right? And then what I have a lot of my players do, especially high schoolers, is they do this shot like this. Their offhand does this. So they're shooting like this. So they actually have two vectors, one going this way, one going this way, colliding together to try to get the ball, because they have one elbow and one elbow, basically, two different directions to shoot the ball straight. So that's my favorite area for teaching shooting, and we'll do that. You'll hear that whole lab another day. So we tried that. Let's do a little vectors here. I am running out of time. We might end up going into tomorrow. We'll see.
So what are you so excited about?
Whoop.
So what are you so excited about?
Well, it's our turn to try a new type of myth, the physics thought experiment.
Great. Something to get the old gray matter working.
So here's how this one goes. Let's say you're driving along in a car at X miles an hour. You throw something out the back in the opposite direction at the same speed. Does it just fall straight down?
Build an air cannon, fire a soccer ball at 60 miles an hour. We'll do it again inside of a moving vehicle going 60 miles an hour. See if the energies cancel each other out, and we get a vertical drop.
Love it. Let's do it.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air. It stops and it just falls.
Look at that.
Fantastic.
I mean, look, it doesn't move at all. It's going straight down.
Woo! We did it! We did it!
So there's another example of two vectors going opposite directions that equal out. So vectors are all around us in that case, and in sports, they're all over the place. Anybody watch the Masters this week? Only one. There we go. There we got two. I watched Tiger play absolutely terrible on. I enjoyed his Monday and Tuesday rounds. I enjoyed watching those, like, every shot of so-and-so. And then you could watch every shot in, like, 15 minutes. So I watched, like, his first 2 rounds that way. Watched the third one that same way. I started to watch it on Sunday, and I'm like, nope, this is no fun. I don't like watching him do that bad. I got other things to do. So where that would work in human movement is you'd have your 2 different directions of force. So force going up, force going horizontal, and then the vectors going that direction. Or, in this case, where it's the attachment would be the force going that direction. So adding this to the levers that we did the other day is where this kind of vectors go in. How long is this? Oh boy, I do not remember what this one is, so we're going to watch it very quickly. Oh, that's right, this guy's fascinating.
Infielders are going to have longest arm action. The outfielders are going to change. So if you go from longest arm action to shortest arm action, typically the outfielders are going to have the longest arm action because they have to throw the ball the longest distance, right? And pitchers as well, because they're trying to throw as hard as possible. Then it goes to infielders. They're going to have a little bit of a shorter arm action. And then finally, you're going to see the catcher's arm action is the absolute shortest because they need to get the ball out as quickly as possible, and they're not throwing the ball very far. So let's look at some of the things that are unique between the infielders and the outfielders. So, and we'll also look at the similarities. So let's just start with the very first thing. The first thing is no matter the position, the ball always comes to the middle of the body, somewhere right around the chest area. So you can see both players, we have Willie Adames over here, we have Cody Bellinger over here. Both players are going to get the ball, they're going to bring the ball to the middle of their body. All right, so that's the first thing. And again, this happens for every position. A pitcher is going to come set somewhere in the middle of the body. Infielders and outfielders are going to do the same thing. Catchers are going to transfer in the middle of their body as well. Sometimes people think catchers take the glove and bring it up into the air, but most catchers will bring the ball somewhere towards the upper chest area, right in the middle of their body, and that's where they're going to break the transfer. So that's the first thing. The second thing is when they take the ball out of the glove, what you're going to notice is that the fingers are going to be on top of the ball. So my fingers are on top. And that is key. And that might seem simple, but there's a lot of players, especially young players, that take the ball out all different ways. And if you take the ball out other than this, in my experience, it's going to lead to an arm action and an arm circle that you're not really going to want. Now, this is where it starts to get different depending on the position. So we take the ball out, fingers on top, and now we're going to see 2 totally different arm circles right here. So you can see Adames on the left is keeping the ball much higher, whereas Bellinger on the right is dropping the ball down below his waist. And again, think about the position, what that position requires for throwing. An outfielder is going to throw the ball much further, and I'm going to basically bring below his waist. Okay, so that's the first difference you're going to see. The second difference that you're going to see is that typically for an infielder, because they don't have to throw the ball as far, their shoulders are going to be more level. Right, you can see Adames' shoulders right here when he goes to throw are basically level. Whereas Bellinger, when he gets ready to throw, his lead shoulder is going to be a bit higher. And so way up here. And now we go over here to Wendell. How everyone is pretty similar when it comes to the infield. And now we go over here to Wendell. Right, same idea. Brings the ball to.
So where that goes to, that's a kind of a biomechanical analysis there too. But where we're going with that is with your vectors in sport, you have to adjust for gravity. When I teach throwing to little kids, I'm like, make a tee, pick an apple out of the tree, and I say point to your target, and they almost always will throw it like at the feet of their target or at the base of the wall. So I always have to tell them, aim above your target, and that makes their shoulders move up to get that motion out of them. So that vector is actually going up until gravity and air resistance makes the ball not go as far. So linear motion for projectiles. So there's many examples in sports. So a high jumper aims for height and distance and rotation so that they can clear the bar. Tennis player tries to land the ball in the correct place in the opposite court. Let's see. In events that incorporate flight, several factors also can take effect of that. So linear motion has 3 factors. The trajectory angle, then the speed or release or takeoff, the height at release or takeoff. So then speed, velocity, height, angle, release are all intertangled there and interrelated. So making that, the height of release, the angle of release is going to determine where it goes. Same thing with the takeoff angle of a long jump. They're trying to get that center of gravity to go the correct height there so that it goes as best possible. So we're going to end on that. Oh, by the way, that's the app. I'm going to try doing some baseball stuff here with some of you.